Okay, hi everybody. I will commence this week's quantum computing seminar with a talk about the ZX calculus or ZX calculus. Switch some stuff over here. Nice aspect of this sort of format, and believe me, I'm not going to go through the whole thing with pre-written notes, but just to go over some of the background that we've already covered, just to have it readily available. So far we've talked about, just in sequence, a lot of different things: symmetric monoidal categories, dagger categories, monoidal structures, comonoidal structures, Frobenius structures. Just to sort of give a quick recap of some of the like basic things that will be important is that when we talk about an observable structure, so for some object Q in a category, we have this sort of notion of copying. I should mention this because the references are all over the place. We've normally been following Vicary Heunen. For this particular talk, I've been more following Koke and Duncan, whose the exact details of that reference are in the abstract. So they go top to bottom rather than bottom to top as Vicary Heunen do. So sorry if I will follow this notation for now. An observable structure is we have this sort of copying operation, and also we have this, I guess this was a unit, sorry. Yes. And then there's some additional compatibility structures. So you can copy and then copy, and that's the same thing as doing it the other way. The dagger buys us the ability to go from a copying operation to somehow like a deleting operation, going from two inputs to one output. And then also the epsilon dagger, plus additional conditions which make sure that everything sort of meshes together. When you have this sort of compatible comonoid and monoid structure, you have a Frobenius structure, so something like this, and they again have to play together somewhat nicely. So one thing that I did mention last time that I sort of want to like return to, because it will become fairly prevalent in the ZX calculus, is this notion of phases. So I mentioned this somewhat last time, but I don't think that I gave it its due justice. So we have this sort of preparation. Let alpha be some map from I to A, and let that be a state. Then we can define a phase map as a map from A to A, such that it has this sort of structure here. We initiate alpha, so alpha is the map from I to A. This is a state. And then we employ the deleting operation. So this is going to be the monoid part of it. And what we get is this composition is called the phase map. So one of the nice properties of this thing is that, so we can sort of think of this phase map as applying a phase, well, at least in the finite dimensional Hilbert space context, we can think of this as applying a phase to our states. One thing that you might expect is that there's some sort of nice way that these things play together in the following sense, which is that if I apply two phase maps, which I can expand using this definition like so, then actually through a sequence of isomorphisms just coming from this sort of Frobenius structure here, we can actually show that these things end up like this. So I don't want to go through the whole thing, but more or less the idea is that I can actually bring alpha and beta over to this branch up here, and then I can combine them. So actually we have that the phase maps form an abelian group. And then you can flip the other direction just by reversing the steps. So we have this sort of very nice structure. in fact, we'll just give a name for this basic structure here, which we'll usually give right like this. And so right now I'm using the colored dots because I was able to prepare this in advance. In the future, the green will be open circles. So maybe I should just give an example, something like this, and I will put an alpha next to it to show that this is a phase map applying the angle alpha. And so there's some properties for these that come from the fact that this is an abelian group. When we take the dagger of this thing, it negates the angle. When we apply it twice, which is essentially what I was doing up here, then the angles will add. So there's the group structure, and the fact that it's additive means it's abelian. Very nice. This turns out to be quite nice when we look at diagrams of the following form. So say, more or less, the idea is that say I have some diagram with m inputs and n outputs, and everything on the inside is just things that are either, green dots or things with or phase maps, and maybe or just wires and such. So this is called the spider theorem. And what it tells you is that there's a sort of normal form for diagrams of this form where I can just condense all of these green elements into a single green element, which is the sum of all the phases. And we keep the input and output structure the same. So there's still m inputs and n outputs. So this, more or less, what this implies is that we can sort of combine, this spider theorem tells us that we can combine green dots together. So if I have something like open circle like this, and say this is, well, we already know that this one is true, but I can also do stuff like this, and these will all just be more or less like this. So this is quite a nice result, so I wanted to emphasize it. I think that I neglected to talk about it last time. Just to see that it sort of works as you would expect it to. What is the zero? So what happens when you apply a zero phase? Well, by definition, this will be some zero state. Maybe I changed up notations just a bit. But by the spider theorem, that tells us that we can collapse this to this. And then we also just have that since this is a zero and this is a zero, that's just an identity gate. And there you go. You see that applying a zero is the same as an identity, which is exactly what you would hope for. Strong complementarity was when we have two interacting Frobenius structures. Now we have to distinguish them. Green in the references, I will use as a open circle, and then red will be a closed circle. We call something classical with respect to a particular Frobenius structure if it copies. So a state K is classical with respect to a particular Frobenius structure if you can copy it. And then we can also define just when two Frobenius structures are strongly complementary, yes. I think that the more important thing to emphasize here is that there's these sort of diagrams that we will impose as we will see rewrite rules for the ZX calculus as additional structure that we need to impose on like a dagger symmetric monoidal category. So one of them is something like this, and then it's color reversed version. Also, we have a diagram like this that we might use. So I think that sort of catches us up more or less. Okay. And actually, I want to go over here. Okay, this is the last part that I will do just because there's a good amount of writing that maybe I want to avoid. So I want to formalize the ZX calculus a little bit. So let's define the notion of an open graph. An open graph is going to be a triple GIO. Here you have an undirected graph G with a vertex set and an edge set. And then also you have subsets I and O, which are input and output vertices. Additionally, we say that the union of I and O is called the boundary of G, and V quotiented by the boundary is called the interior, or with the boundary removed. And this is the last thing that I kind of want to get away scot-free by just revising the notes that I've already done. And so a diagram is an open graph. So we're defining a diagram in this case. A diagram is an open graph where all the boundary vertices are of degree 1. That's basically just saying that you start with some states and you end with some effects or measurements. The inputs and outputs are totally ordered so that we can think of perhaps going from left to right, that we can talk uniquely about the kth sort of input for a particular arrow or box or vertex, as it were. Inputs, outputs are totally ordered, and the interior vertices are restricted to have a particular form. And this is wrong, so these should be colored in. And so I should actually elaborate on what this is. So this is, I have all, just based on this spider theorem that I wrote down, basically this is the result of using the spider theorem, and everything that's on the interior of these open graphs are going to have the form of, you have some sort of vertex, and alpha is the total angle there, and then there's n inputs and m outputs on this thing. Similarly, just with the colors reversed. And this is the one new element, which is suggestively labeled H, which is restricted to be a vertex of degree 2. We sort of give it its own little notation H, and this will eventually be related to the Hadamard. Oh, there's a question. Very nice. Will the recording be uploaded? Yes, to my knowledge, it will be uploaded.
Selman, sorry.
Sure.
Yeah, so these alphas, so for any angle alpha, you have one of these operations. Is that what's going on?
Yes, for any angle alpha.
Okay.
And for, yeah, you were going to say something?
No, I mean, is there conditions on like if you concatenate different alphas, what happens and things like that?
So you have to be a little bit careful when you're doing this with different colors, but when it's
with the same color.
When it's the same color, it essentially just means that you can add up the alphas. That's the content of this.
Okay, which is okay. Great. Thanks.
Just coming from more or less this abelian structure.
Okay.
Okay, so I should. Okay, so let's just introduce this. Let me make this bigger, perhaps. Okay, so let's sort of introduce this category with objects of diag being given by natural numbers. And we have that the morphisms between these things are going to look something like this. These are maps of this form, but it's going to just be easier to draw them. So I have F a morphism which has, so there should be, I don't know why I did it this way, but there will be n inputs to this thing, and m outputs. And then suppose that we had another arrow, which is going to be, say, generically from K to L, then we can actually compose these in two different ways. One of these ways is going to be that we compose them vertically. So if I have, sorry, the other way around. So what is this going to look like? This is just stacking them. So I will assume that m is equal to k in this case. So I will have f. This will be some number of inputs, then some number of outputs. Let's call it m, which should also be the same number of inputs that go to G. And then there's some number of outputs for G. Similarly, we can also think of composing these horizontally. So, and then just drawing them side by side as usual, the tensor product. This is going to give us F tensor G. So we can see, as you might imagine, this G F composed with G is going to give us, say this was N, M, L, something like this. This is going to give us a map from N to L. When we have this composition, this we have that if this was N, M, K, L, then this is going to be, then this one's going to be a map from N plus K to M plus L. So this is more or less what you would hope for. So some additional comments here. So let's make a remark. You can add a dagger structure to this.
Sorry to interrupt again.
No, not interruption.
So, uh, it, so you are saying actually that the morphism from N to M is like one of those diagrams that you drew before with N inputs and M outputs.
Yeah, so sort of, well, what I'm gonna get at is like we basically, and so I think that you'll be familiar with this idea already. So the idea is that you construct this sort of like decorated graphs, more or less. You have this sort of numbers of inputs and outputs, and you might have some additional labeling that goes with these vertices that, I mean, I'm calling them F and G, but F and G just have some numbers of inputs and outputs. They compose in certain ways, just like these dots that I was drawing before. And
Yeah,
more
but
or less, yeah,
also in DAG,
yeah.
like objects are natural numbers, fine. They represent inputs or outputs, depending if it's source or target. The morphisms, like what are like, I don't think you wrote anywhere what's a morphism.
Yeah, are they
You just
graphs? Do they have to be labeled? This is something I
Yeah,
was
they
unclear on
need
as
to be
well.
labeled, and they're also, I mean, so my understanding was that F is the morphism. So the objects are the natural numbers, and the morphisms are maps from N to M, or
okay, so
between natural numbers.
yeah, so let's
Wait,
maybe sorry.
no,
So
go
let's
please.
maybe yeah, sort of complete this I think notation suggests that, okay, so what you drew there, the F and the G and the two compositions, are sort of the abstract way to interpret such type of structure, okay? And
Okay.
out of curiosity, if any of the students or whatever want to expand, this is called a prop, the structure you laid out. So it's a particular type of monoidal category. But
Mhm.
I think what you want to say is that the so a morphism is a graph as defined above,
Mhm.
whose boundary is n plus m, so to speak. Like the inputs are the n ones and the
Yes.
outputs, because you
Yeah,
specify.
no,
So
that's
what you want to
yeah, I
say, I
see
think.
the confusion. Yes, because
Yeah,
those
yeah.
are, ah,
And then you say that, oh, those abstractly, like if I had a graph with n inputs and m outputs,
uh-huh.
we just
Yes.
think of it
Okay,
as this
I
type
see
of
the confusion.
single
So,
morphism. Yeah, because
yes, so we have this open graph, and in principle, what I'm actually talking about is these interior points. Uh-huh. Interior vertices
no,
are
I think, look, what you're talking about. So the F, the little f there that you drew
yeah.
as an example, is the graph. It's not
Is
one
the
part. So F itself is the graph. Okay, so if instead of
mm,
little f, you wrote capital G for a
diagrams?
graph with n inputs and m outputs, that's how. I mean, these are not single operations, but of course, a single
Yeah,
operation could
sure.
also be. Well, I think it violates the definition, but whatever. You must have Hadamart's,
Well, okay, so
yeah,
we can
whatever. Yeah,
actually, I can
maybe
bring up
what
the
as the
definition real
talk
quick, if that would
as the
be.
talk.
No, I think that this is the purpose of the talk.
Yeah.
So the definition is coming from this. Um,
Uh,
uh, the objects are
where is
natural numbers. Arrows are those diagrams with inputs and outputs. Composition is formed by identifying the inputs G with the outputs of F and erasing the corresponding vertices. Okay, blah, blah, blah. So,
So if I remember correctly,
mhm,
uh, Kuka and Duncan give like a fairly strict definition of what they mean by a diagram, which is something like an isotopy class of graphs in the plane that allow crossings, uh,
yes.
and so those are your morphisms then.
uh, yeah, I guess you don't need to we don't need to go to that length of formalism unless we are, I don't know, writing a paper. But
Yeah,
yeah,
and
this from here it says for the collection of diagrams forms a category. You see,
yes,
like those are your morphisms. So
objects.
F and G, as described here, is a graph. And so IF is the inputs of yeah,
Hmm.
I think it's
Okay.
what's
Yeah, I hadn't interpreted that like that. Okay, that
and the dagger is just, I guess, applying or
Well,
just
it's
okay.
reading it upside
So
down.
yeah, it's just reversing the orientation of the
okay,
graph.
so if we were going to
Yeah.
redo this, um,
Um,
what are we saying that this category looks like?
so let's say a morphism, I don't know, from 2 to 3
Okay.
is any graph where you start with 2 inputs and you end up with 3 outputs. Like you can draw any of them.
Okay.
And those can have multiple vertices in them. They don't need to be like a single one with two
Sure,
inputs and three outputs.
many ways to compose it to get actually two inputs and three outputs or whatever.
Yeah, so any such possible configuration of boxes where you in the end end up with two inputs and three outputs is a morphism from two to three. And the way you compose is you just either stick them side by side or you just stick them to each other along inputs and outputs if they coincide. So it's basically composition just means here taking two little graphs and making a bigger one, if you wish.
Yeah, but I don't know, you use the words like big and little. So I mean, presumably there is some sort of basic graph in which by definition it just has these two and three, like, and it's
Uh,
not made up of something more, right?
I mean, those can be hard to sort of individuate. What are the basically you're looking for generators.
Yeah.
So you want to say these are the basic types of graphs we can have, and anything is a composite of these somehow. I mean,
So,
if
I mean, one thing that might be useful is if we keep going, because there is a notion of
yeah,
generators in this formalism.
yeah, I mean, sure. I just wanted to understand.
No, and I'm not
So I
sure that
think
I sort of gave any insight into that. Yeah, I think that you gave me some insight into how this might be working. Um, but okay, so I don't know if we keep going, maybe it will actually make things a little bit more clear, perhaps.
yes, depends on what you want to do with the category. I think it will become clear what the stuff needs to be.
Yeah, so I think what we
Yes.
want to do with the category is a couple of things. One is just, okay, I already said this, but let's, one is just that we can, a dagger structure can be added. Okay, and so this part's going to be left a little bit open for the time being, mainly that we have this actual category that we're interested in, which will be given by quotienting out in diag. And so I will try and explain this as we sort of go along. So here's the basic idea. First, we want to sort of understand what an isomorphism of diagrams is. So is a bijective correspondence. Boxes, wires, which preserve the manner in which the boxes and wires are connected. So that would just be something very straightforwardly. Maybe I could have just given the example. It's kind of straightforward to see what's going on. So if I have some F and some G, I can do this. And we say that these two things are, and we've more or less been already using, I should start this higher up, I guess. So something like this, or for example, is isomorphic to something perhaps like this. These would be examples of something like that. So in addition to the notion of isomorphism of diagrams, we have these additional sort of rules that we want to impose on our graphical language. So these are equations rather. So these are rewriting rules. And so the idea for that is, I'll just say it sort of verbally, these are externally prescribed equations that hold in the graphical calculus. So what we can sort of think about is, suppose, just to give an example, is say I have that F and F dagger are equal to the identity, so that, you know, this is what we would call unitary. It's defined, this equation precisely defines it. And then say that I have some sort of messy looking thing that looks like this. Let's actually say we have G like this. And then say F dagger like so. And out. So the basic idea here is that there are these notions of cutting this diagram. So I can cut this diagram horizontally. And this horizontal, so the either end of this horizontal cut will give me a valid diagram. On the other hand, I can also think of cutting something vertically. Now, it will not be the case in this, since I'm actually going to be going up to this box G, doesn't necessarily have to be the case that this vertical cut here is, either side of that is not necessarily a sub-diagram or a valid diagram in any sense. But the basic idea is that we want to sort of be able to isolate sub-diagrams, like for example, this one. And what I want to do with these rewrite rules is just to say that I impose this equation by fiat. And so what I can do is, in a bigger diagram that's composed of these sub-diagrams that I can obtain from cutting horizontally and vertically, that I can sometimes take this sub-diagram here and just say that this equals that coming from over here. So that this whole thing is actually just like this. I used a rewrite rule to just simplify this according to, you know, the equations that I'm imposing. So I want to go back to what I said here. It's going to turn out to be the case that this equivalence relation is, I defined these basic sort of these basic diagrams, and the diagrams will be occurring in a dagger symmetric monoidal category. But in addition, I want to impose additional structure in terms of some sort of rewrites. So more or less what this quotienting is doing is saying I have a list of equations, and I'm making sure that I identify all of the diagrams that are equal after application of the rewrite rules.
So yeah, again, just to clarify,
Mm-hmm.
so what's going on seems to be that you have an initial relation. So in the example you drew, so you have an initial relation on morphisms,
Mm-hmm.
and you just say that you extend it by composition.
Yeah.
So that would do it. Like then the example, the more complex example you drew, I mean, you can see that graph you drew with the F and F dagger above
Mm-hmm.
as a composite of two graphs, where you have
Okay.
just the F and F dagger, and then the other one where there's the bride and the G. Yeah, I guess. And that would be a composite. So if you extend the relation through composition, then it gives you what you want. Yeah, just saying.
Can you unpack what that means? Sorry, when you say you extend it, can you just
I mean, in
I
general, if you
mean,
have,
another
yeah,
way of looking at it is in much the same way that you can give generators and relations for a group.
yeah.
What you're
Okay.
effectively doing here is you're saying we have these basic things and we have some relations that we already know hold, and then you're freely generating subject to those relations. But
Mm-hmm.
that means that I think that what Reggie means by extending the relations is that you have to then also consider applying those relations to parts of a larger composite, which gives you relations on larger composites when you freely.
Oh, I see. Okay. Yeah, that's what
so yeah,
maybe that's okay. Yeah, I see what you mean. Yeah.
okay, so what I meant by extending by complete is that you have a category and say you have a relation on
Mhm.
morphism fits.
Okay, so can
Uh,
I try and paraphrase what I think is said
okay,
here? It's like the fact is that I can look at when I look at this diagram here, this diagram here is the result of horizontal and vertical compositions, say, and
no, no,
okay,
that,
and
so
so
it's a good point to illustrate what we were talking about actually. That diagram itself is a morphism from one to one in
yeah, it's from
diag.
1 to 1. Yes.
So that the whole thing.
Hmm.
And so now the big graph can be seen as sort of, I don't
I
know, a
guess
3 to 1
3 to
where you have
3 or
identities. No, a 3 to
oh,
3
I see.
composed
Yeah,
with a
the
3
before
to
the
3.
horizontal cut. Yeah.
And then it's sort of, there's also the horizontal composition. And if you just say that we extend the relation through horizontal and vertical composition,
Okay.
uh, then, because you need that to do the quotient. That's why, because you put a relation that needs to be compatible with composition. And the
Yes.
easiest way to do that is to say, I'm going to specify these generators, as Walker was saying,
Hmm.
and just extend by composition so that I don't have a problem.
Okay.
So
Yeah, I
if
see. I
if
see.
yeah, if I compose something with two things in this relation, I will say that the resulting two things are also in the relation. Just say that. And so the same thing with the tensor product. Yeah.
Okay. Yeah.
Uh, yeah.
Okay.
Just
Makes
to,
perfect sense. Um, okay. So now I'm gonna be doing my laziness here, but there's a bunch of rewrite rules. So I'm just going to one. Oh no, I don't need to go there. So, okay, so I just want to sort of dig into some of these. Some of these we've already talked about. More or less, you can combine if it's like color and it's got M inputs and outputs, you combine them and you add up the phases. So this is something that you impose. The fact that this is the identity, you have these sort of copying relations coming from the interacting Frobenius structures. And then you have some additional structures coming from the hop structure. And well, okay, so I also want to talk about these H's because I guess intuitively people who have seen the physics know this because what H does in terms of like matrix algebra acting on like Hilbert spaces is it flips you from the 0, 1 basis to the plus minus basis. So this is encoded over here in just saying that if I have H and then I copy in the green color, that's the same thing as copying in the red color and then applying H everywhere. So basically you can commute H through, you can always commute H through, but it flips the color. That's how it works. And it's also self-adjoint, so you just have that it applied twice is the identity. And so this one I have to, I mean, this one makes sense, but I have to remind myself if this is where this is coming from precisely. Oh, and there's another one that is not here, but it might be derived from these. is that there was this notion of a cap, and we want to ensure that the cap with green color and cap with red color are equal with each other. If you're familiar with the physics, you know that your Bell states, which is what the caps correspond to, look something like this, which when you expand it out is the same thing as plus, 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 minus, minus. So this is another one of those rewrite rules. Okay, so we should go like this. So one of the ideas here is that I kind of like that they emphasize that is that we have that the ZX calculus. I don't know if is the right word. Is a functor. Not sure if that's actually the correct terminology here, but the basic idea is that you define this functor here, d to f hilb, such that we have to satisfy this action on generators. So ZX acting on, let me think for a second, the identity here. Yes, needs to be equal to C. Some other ones, we have to have that the image of ZX on this H is precisely equal to the Hadamard H. We also have that ZX of alpha should be precisely equal to rotating about the z-axis of the block sphere. So you have a unitary that looks like this. 1, 0, 0.
Sorry, either, so I think the first line should be C2. I think it was also written above because the Hadamard is from C2 to C2, right?
Hadamard C2 to C2, yes. Oh, this is an identity object. Sorry. One moment. Let me make sure that I'm putting. Oh, is this supposed to be just empty like this? Oh, yeah, maybe sorry, that's a typo on my part. It's just if I just have the 0 to 0 object.
Yeah.
Sorry. Don't know where
that
yeah,
is,
I think I was thinking in reverse. I know that this is the unit object, so I wrote I over here. Anyway, yeah, that was a typo. Seems reasonable. Okay, thanks. Good to know. Is a functor. And then we also have that ZX of alpha is equal to, just remind myself how I wrote this. Oh, okay. This is not a generator. Well, it's not, it's a special instance. Okay, there we go. So we have these basic components, M, N of alpha, which was something like ZX of and this here is alpha. How does this work? This is going to give us 0 to the M goes to 0 to the N. Okay, yes, this is what it is. And then 1 tensor to the M. And we're applying the phase gate. The Z rotation is going to apply e to the I alpha to 1 tensor to the N. Similarly, you might expect that we know what this is going to do. It's the same thing with colors exchanged. Ourselves. Okay, so very good. Yeah, so one thing that we can say here is that, I mean, at least from my perspective, is that more or less you have this sort of abstract left-hand side, which is this category here, and then you have FHILB, and more or less what this functor is doing is it's giving you an interpretation of how to understand these diagrams in terms of something concrete. So this sort of assigns an interpretation to the abstract symbols we were using previously, which I think is a nice sort of perspective on it. So there's this theorem so that for any diagrams D, D prime in D, if D equals D prime, then we have that ZX of D equals ZX of D prime. Now this is apparently called soundness. So people will say something like in the jargon like ZX is sound. Just basically any two diagrams, if they're equal, then the image in terms of linear maps on your FHILB, these will also be equal. In a similar vein, we have that if you have some D, which is a diagram, then ZX of D dagger is equal to ZX of D then dagger. However, there's an important sort of caveat here, which is that ZX is not complete. So, which is just to say that it's possible to have two diagrams whose images are the same. So you have some D prime such that ZX of D equals ZX of D prime, but D is not equal to D prime under our system of rewrite rules. Okay, so related to this, just sequence. Oh, go ahead, Reddy.
Yeah, so by being complete, I mean, perhaps is the statement saying that you cannot, I don't know, write a finite number of relations such that ZX would be like, so that will not happen? Is there a statement like that that you read anywhere? So, because, I mean, you impose these rewrite rules,
Okay.
then you say, okay, ZX respects those, meaning if you can go from D to D prime with rewrite rules, ZX does the same thing. So that's good.
Yes.
Now you're saying the reverse doesn't happen.
Yes.
But the weird, I mean, saying it's not complete, I don't know. So is there a thing of the form where you cannot write a finite number of rewrite rules such that ZXD equals ZXD prime would imply D equals to D prime? Is there a statement like that?
I don't
That
know
you
about the
know of,
finite number
or
of steps. What I think I can do for you is find an example in which this happens to be the case. I don't have it
okay,
off the top of my head, but my understanding was just as basic as what's stated here. And I
Okay,
know
okay.
I saw an example of this form
Okay.
at some point, but
No,
I'll
just curious if it's known sort of for
yeah, so I
the
don't know how they actually prove this in complete generality. I was assuming that there's probably some counterexample that people are aware of, and that suffices. I don't know if there are some general results about the completeness of ZX or how you can make it complete and stuff like this.
yeah, like no-go theorem type of
Yeah,
stuff. Yeah.
yeah, this sort of business. If I remember correctly, this is a paper by, let me put it in. I want to say that and maybe it's a sequence of papers from the mid 2010s about the completeness of ZX. So for the interested reader, they can take a look at those. I myself haven't looked into them too deeply, but maybe after this week I can. So, oh yeah, so, but there is another sort of, this is just basically a sequence of results about ZX now. But this is coming from something outside of that, which is that the following matrices, or quantum gates, are universal for quantum computation. So what does that mean? So if I have something that looks like this, Z, just to make it look like the other notation, if I have a Z that looks like this, if I have an H that looks like this, which I already wrote, and I have this thing called a controlled knot, which is going to look diagonal here, off diagonal here. For those that remember, this is I, X, 0, 0, something like that. These are sufficient to represent all unitaries on C. Okay, so this is something from outside of ZX, but as a corollary to this, we have that ZX calculus can do the same thing. And the basic sort of structure here, I mean, this is not a full-fledged proof by any means, but we do have some basic sort of things that we can write down. We have that ZX of H is precisely H. Okay, so that's trivial. You have that ZX of this map right here is precisely Z alpha, or I think I wrote it like this, right? Okay. And then there's another piece, which is, I will address this in a, okay, then there's also the C naught, which ZX of is CX. So you can represent all of these primary constituents in terms of the ZX calculus as well. So you have that. You could say that ZX calculus is universal for quantum computation. Some sort of phrase like that is not incorrect. Let's get to some examples where we sort of use these rewrite rules to prove some, I guess, well-known things, but this is a sort of more graphical illustration of this. So there's this thing called the CZ gate, which just write down something like this. And so what's gonna happen here is the following. I have the following rewrite rule. I can flip the color of this. I can flip the color of this piece at the cost of introducing, I can permute this one through at the and then I change the color. Or additionally, I have one of these rewrite rules that I will see if I can find. Oh, it's on the other one. Yes, this one right here. I can move something through a green at the cost of flipping its colors on all of the branches coming out of it, or vice versa. So what that will do is I have this here. When I move, when I want to flip this to green, I will introduce an H here. And then it will introduce an H precisely here and here, but H squared is identity. So we have that this is open circle like this. What's kind of nice about this is that you see that it's symmetric on its inputs and its outputs, which we know is the case for controlled Z. Let's see some other examples. Let's skip that one. Some other examples. We have something like, let's show that controlled x is controlled x squared is the identity. So what we can first do is we can squeeze these together by this spider theorem, more or less, which just tells me that I can put light-colored things together. So I have like this, and I have this. So this is from spider. And then I have, so maybe I'll flip around, see if it's here. I have this piece here. Now, to be completely honest, this seems like I have to think about this piece a little bit more. It appears to me that you can do these going sideways, which is not immediately obvious to me, but I believe that that's what's being done in this next step. So I have something that looks like the one that I just wrote or that I just showed. So it's this one right here. And then it goes into two disconnected pieces. So I will have something like, but these don't have any angles next to them. So they're applying just the zero phase. So this is just like that. So this is a bit of a question mark for me. Personally, I have to think about that a little bit more, but I believe that that's what's being more or less done here. There's some other sorts of gates that we can add. Okay, so we can return to our old pal, the teleportation gate. So in this particular implementation, because we're only considering this case where we haven't introduced this non-deterministic element where measurements can branch out into different sort of outcomes with some probability, we're going to sort of do a sort of assumption that we're post-selecting on particular outcome. So when, by which I mean just that we've performed the measurement and we're saying that we have obtained a particular set of outcomes for it. So if I have white, red, cap, beta, alpha. Now, beta and alpha are going to represent the outcomes of my measurement. H and alpha. I don't need to put that in. something like this. So I can play some games here just by using these rewrite rules. First things first, I can flip this into a red color because of this this combination with the H. So this will be alpha, beta, alpha. Okay, so now I can actually combine these two like so. So I actually have that this is alpha, beta, beta, alpha. Okay, and what we see now is that, should I have changed the sign on one of them at some point? Yeah, I think probably I should have changed the signs on these because, of course, in the actual teleportation, you have that some unitary is applied on the outcome of the Bell state, and you want to undo it, which is going to be the complex conjugate, so which will correspond to the opposite negation of the phase. Sorry, the mistake on my part. So. And you can see here, I have red and red, they will combine. I'll have a 0 phase and then also here as well. So I just get that tried and true single line. Okay, so one last thing to sort of wrap things up. Okay, the measurement calculus, just roughly, the idea is the following. You have certain sorts of basic operations that you can perform. One of them is preparing, and now I think that I've switched my convention. This needs to be related to a plus state. Just for convenience, I will flip the color orientation. I can also perform a controlled Z gate, which let's put this in here, E, I, J, and also I can perform a measurement like so, Mi alpha, this one corresponds to minus alpha. If this is a plus state, then this is measuring in the this is measuring in the 0 plus e to the minus I alpha 1. So these are your basic commands. So how does this work? If I want to actually execute a particular sort of unitary, then what I can actually do is prepare a bunch of qubits in the state n using the n command. I entangle them, and then I perform some measurements. And this will actually perform a unitary. So I would just want to give you guys a flavor of how that works in terms of just an example. So say I take a command like the following. Oh, just to give you guys the punchline, what I actually want to do is the following. I want to implement a single qubit gate from C2 to C2, which is a single qubit rotation. As an additional fact, you can generate any given single qubit rotation using just measurements along the z-axis by some measurement angle gamma, measurement around the x-axis by beta, and measurement along the z-axis again by alpha. This is Euler decomposition. So consider the following command, which I'm going to tell you now just to give away the punchline, is going to perform a single qubit rotation. What I will do is the following. I have M3. In principle, I should read this right to left, so I will do that. So we have N5, N4. This is just me telling, giving the commands to prepare each qubit in a certain state, and then I entangle certain qubits. Qubits 4 and 5, qubits 3 and 4, qubits 2 and 3, qubits 1 and 2, and then finally I measure them M1, the first qubit with angle alpha, according to this convention up here, to beta, M3 gamma. And this thing is going to precisely give me the single qubit rotation that I told you guys it will. And so we can actually use ZX to see how this works. So let's just, first of all, how many qubits, how many input wires are we going to have? Total of 5 qubits. So one of them will be an input state that we want to teleport, or the basic idea will be as follows. So maybe I can actually bring up the one that I've done just to give a flavor of how it works, which is like this. So I have 5 qubits, and it requires, you can actually have MBQC models with less than this, but the basic idea is that I have 1, 2, 3, 4, 5 qubits. Some of them I've used the command, this N command, to prepare a plus state for each of them, and this one's left free. This could in principle be some abstract, just generic quantum state psi. And then I have these entangling gates. So I have 1 and 2, 2 and 3, 3 and 4, and of course these actually all commute with each other. So because of the properties of CZ, so I just did them in this order, and then 4 and 5. So based on our rewrite rules, what can we do here? We can combine stuff and just add up the phases. Boom, 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 boom. So we can squish this down to just alpha, H, beta, H, gamma, HH. Well, this is just the identity, at least in the image of ZX. And then we have that there's the possibility of moving this over at the cost of flipping the color. Okay, but this is precisely what we wanted to implement. A rotation around the Z axis, rotation beta along the x-axis, and a rotation gamma along the z-axis, which is precisely going to apply that single qubit rotation to psi. So this is, I thought, pretty neat.
Beautiful.
Yeah, I mean, so Reddy, you get to appreciate just how much nicer this is than when I tried to explain it maybe a few months ago in these Wednesday meetings. So this is much, much cleaner, much, much nicer. You see within 2 lines that that's the only thing that it can be.
I mean, it's also like the diagram itself. I think it's explanatory of the process you're trying to implement. And then the rewrite rules tells you it's what you would think it is.
Yeah. Okay, so actually, there was a couple of other examples that I had, but I think that this is a good place to stop. Any questions? Let me check the chat. Nope. Okay, very good. So next week, the talks will again be on Zoom. It will be about Okay, so it'll actually be a very interesting sort of somewhat distinct change of direction, but I think that there are connections to be made to this. When I look at MBQC here, I am kind of restricting myself to, as you can see here, actually the measurements should in principle be non-deterministic, and then I actually have to do these corrections. So I've been sort of suppressing the corrections part of it or the non-deterministic part of it because actually that requires a little bit more sophistication for how to introduce that sort of thing. I think that one approach to actually fixing that and having the non-determinism is to go to this Peter Sellinger's CP sort of formalism. So instead of pure states, like just pure bras and kets, you have a density matrix, and instead of unitaries, you have completely positive maps and things of this nature. And that is one way to actually reintroduce the non-deterministic flavor of something like MBQC. So I will try and make that connection between the two things. But for the most part, next week it will be about the CP construction, and let's see if we can make connections to MBQC as well. Okay, thank you.
So I've asked all my questions during the talk. Just wanted to thank you for the nice talk.
Okay, thank you very much, Reddy. We're continuing our dialogue. It's
Yes.
okay. Well, I'll see you
So,
guys I guess shortly or a
well,
little
so actually, can you, Rady, and Victor stick around for just a second so we can figure out what precisely to do?
Okay, very good. So or maybe what I can do is end this and then we can just restart it. Just
Sure, yeah, sounds good.
okay. So just come back into the chat room in like a minute.
Sounds good.